Hey everybody! In our last video, we talked in depth about looking for continuity when using the graph itself, a visual representation of a function. So tonight, what we're going to do is we're going to look at some functions where we don't have the visual graph to support us. So we're going to have to be able to look at the function's formula, the equation of the function, and be able to determine from the equation whether this function is continuous everywhere, or we're going to look and see where maybe this function is not continuous at. Here we have a theorem, and this theorem is very important. It says, let me read above, algebraic combinations of continuous functions are continuous wherever they are defined. So if you have a small piece of a function, you say, this piece, I know, this is a straight line. This is continuous. Now, if you take that straight line and you combine it with another straight line, two continuous things, when you put them together, are continuous wherever they are defined, wherever the function has value. Which, remember, in continuity, if the function value doesn't exist, it's not continuous. You have to have a function value to have a point there. All right, so here's our theorem. If you add two continuous functions together, they're continuous. If you subtract two continuous functions, they're continuous. If you multiply a number, so let me show you right here, number 3 here, this k, is a constant multiple. So if you take a number and you multiply by a continuous function, it's still continuous. If you multiply continuous functions, we're continuous. One that you're going to have to watch out for is when you divide two continuous functions, because this is where you start having points where your function's undefined. So in this case, you're going to be watching for when the denominator, erase that, fix that. When the denominator is equal to 0, we have a problem point. As long as the denominator is not 0, we're continuous everywhere. If the denominator is 0, the function, the division of the two functions, is undefined, and that is a point where we would have a discontinuity. Number 6, powers. If you take a function and you put a power on it, it's still continuous. Now, that power would be positive integers, so like 2, 4, 3, 7, not negatives. Negatives would create a fraction, so you'd take the reciprocal, and not fractions or decimals, because that would create roots, which also create a whole other thing, which is number 7, roots. So square root, or the nth root of a continuous function, provided it is defined on the interval containing c, where n is a positive integer. What does that mean? Okay, back up. So remember, when you take an even root of a number, you have to have positive values inside. So suppose f could be a negative number. Well, then you have to restrict the domain of the new function that you've created. I'm going to show you an example of that in a few minutes. So just be careful. If you put an odd root on a continuous function, no problem. It can be defined anywhere. If you put an even root on a continuous function, then you have potential issues depending on what the original function was. All right, so let's look at some examples here. Basically, I'm going to show you what to watch out for. So we're not going to break this down completely. So first of all, this right here is a straight line. It's a linear equation by itself, 9 times x. So that is fine. That's just linear. Okay. Next, we have this guy here. Well, he's a linear function divided by linear function. So those two pieces individually are continuous, but we've created a denominator. The denominator is not allowed to be 0. Our function would be undefined if that happened. So let's find out what x value we're not allowed to have. Because if we plug in an x that makes this equal to 0, then we have an undefined point. All right, so I took my denominator. I set it equal or not equal, doesn't matter. As long as you understand you're looking for what's not allowed. Bring the 7 around. So negative 7, bring it around, becomes positive 7. So we've just learned that x cannot be 7 in this new function we've created. All the individual pieces were continuous, but when we put them together, we caused a problem point, the x equals 7 point. So we would say here, if I were to write this out, f is continuous at all x's not equal to 7. So anywhere except that x value, this function's continuous. So first of all, watch out for denominators. Denominators cause problems. All right, part B. Do you see the issue? Well, in the top part, we actually have a linear function, so that's continuous. In the bottom part, we could factor this. If we factored this, we would see that we had two linear functions multiplying. So individually, everything is continuous. The problem comes in to the fact that we have a denominator again. So let's go ahead and factor the denominator. That way we can see what's actually down here. So if you need to review factoring, it's very important. I suggest you go watch some videos on factoring. There's no number in front of x squared. We have three terms, nothing in common. Okay, so break up the first term. X times x is x squared. Now what numbers multiply to be negative 12, but add to be this 1 in the middle term? We need positive ones. So let's see, 4 and 3 would work, but I need them to add to be positive, and I need them to multiply to be negative. So there you go. This is our denominator. So what we've just learned here is that our denominator is not allowed to be 0. That would be where this function is undefined. And we're going to solve this. Remember, if you have a product of two parentheses, so we factored the parentheses, factored the denominator out, set each one equal to the 0, and you'll be able to solve to see what x values individually make this denominator 0. So we end up with x is not allowed to be negative 4 when we bring the 4 around, and x is not allowed to be 3 when we bring the 3 around. So what does this mean? If I took negative 4 and I plugged it into this problem, I would end up with an undefined function value. If I took 3 and I plugged it into this fraction, I'd end up with an undefined function value. Both of those places would be places where this function is not continuous, because the function would be undefined there. So we're going to say here f is continuous at all x's not equal to the negative 4 and the 3. Any other x value you plug in, negative 4.1, 3.5, anything else would be fine. We'd be continuous there because there's no problem point here. There are some other things you have to watch out for, but these problems haven't given me an opportunity to show them to you yet, so we'll build up to that. All right, so the next one I want to look at is sine of x over 3x. Is this function continuous? Well, remember, look at them individually and then divide. Is sine of x continuous? So sine of x, if you recall, is just a curve that goes like this forever and ever and ever and ever and never stops. No breaks, no gaps, no jumps, no holes. It's continuous. Just a reminder that sine and cosine are basically the same, just shifted. The issues when it comes to trig functions would be tangent, secant, cosecant, and cotangent. These all have points where we are discontinuous. So these are not continuous everywhere. They are discontinuous at particular points. And that's something you might want to review. It would be very helpful to you to have a fresh idea of what trig functions look like. If I will review them when we come up to a couple of those, but you might find them popping up in homework. I can't review everything in these sections, so I'm just reminding you, those are different functions that are discontinuous. You might want to go refresh your memory where those discontinuities are. Okay, 3x on the bottom, that is again a linear function. It's just a number times x, so that's continuous. So the top's continuous, the bottom's continuous. So is this continuous everywhere? No, again, we have the same problem as the last two. We have a denominator. So our denominator is 3x. What is the denominator not allowed to be? Hopefully you've caught it on. 0. Always. Cannot be 0. So if I divide both sides by the 3, what have we found? We found the point where this function is not continuous. So we would state here that y is continuous at all x's that are not 0. Okay. I think I have one more here, maybe two more. Okay. So here we have a root. First, let's look at what's inside the root. Is what's inside continuous? This is just a linear function again. So again, this is a continuous function. It's a straight line. Does an odd root cause us any problems? So that's the question that you have to ask here when you look at a root. Odd roots do not restrict our domain. So a root does not actually cause a discontinuity so much as simply restricts where you can be continuous, because it restricts what x values can actually be plugged in. So if you had an even root, let's make a side note here, if we were looking at maybe the fourth root of 3x minus 21, then we would restrict our domain. And how would we do that? So inside an even root, the inside, all of it, so 3x minus 21 is what's inside. The inside of an even root has to be positive or equal to 0. The even root of 0 is 0, so that's okay, but it cannot have a negative number. So what you would do in this case is you would take the inside, set it greater than or equal to 0, and you're solving for what x is allowed to be. So bring your 21 around, so that's positive, divide by the 3, and we find that our new domain is x is greater than or equal to 21 divided by 3, so 7. So f is continuous on our domain we found. Sometimes you can have a root and a fraction together and you have to combine the two, but I'm going to let y'all try those, and you can reach out to me if you have any questions on that idea. It's something good for you to experiment with before I tell you how to do that. All right, so one more example here. This one is called a piecewise function. Why is it called a piecewise function? Because there are two pieces to it. The first piece, the fraction, is the formula that you use if you plug in an x that's not -2, so anything except for -2. If you're plugging in -2, then you use the second piece of the function for that x value only. Okay? All right, so how do we deal with this? Well, let's look at one piece at a time. Is this main piece continuous? Well, on top, we have a polynomial. Polynomial is just linear functions multiplied together. So this polynomial, he's continuous. On the bottom, we also have a linear function. He's also continuous. The problem is when we divide. Again, we have a denominator. So we have a denominator and we have a piecewise. Two issues that we're dealing with here. All right, so first denominator. X plus 2 is not allowed to equal 0. That would make the denominator 0, which would make the function undefined. So we have this is our point where f is discontinuous. So let's look at that point. So x is not allowed to be -2. Oh wait, we already said x is not allowed to be -2 there, right? So is this actually a problem? No, it's not, because we're not even looking at that function. But what's happening there? This is something that we are going to be talking more and more about, but I want to talk about it starting now for this problem. When you have a function like this one, where you plug in -2 and your denominator is undefined, you need to know, is that a vertical asymptote or is that a hole in your graph? These are very different issues. A vertical asymptote is not a removable discontinuity. We talked about that in a previous video. It's an infinite discontinuity. It is not removable. On the other hand, a hole is just one hole, one open circle. This is a removable. I don't know which way to spell that. Discontinuity. Covered my bases. Covered it. Spelled it both ways. I think I should erase that E, but oh well. Alright, so which one is it? How do we tell? Well, what you're going to do is you're going to take that function, that fraction, and you're going to factor top and bottom and try and reduce it. So x squared plus 5x plus 6 over x plus 2. So let's factor the top, 2 parentheses. So x squared becomes x and x. I need two numbers that multiply to be +6, but add to be +5. Plus 3 and plus 2. All right, so here's how you determine if it's a vertical asymptote or a hole. A hole, you can reduce or cancel out. can we cancel out the whole? The x plus 2 can cancel from top and bottom, and you're left with just x plus 3. Is that cool? So this is, in fact, a whole at x equals -2. The question is, does the second piece of our piecewise function fill in the whole? So how do we determine that? We're going to plug x equals -2 into our reduced fraction. So take your x plus 3 that you just found, plug in your -2 for x, and we end up with what answer? 1. That's what they have here. So they have, in fact, said, okay, the first function, the fraction, has a whole at x is -2. The whole is actually at what we just found, 1. So let's just define that the second piece, if your x value is in fact -2, you're going to put a dot at 1. So we filled in the hole here. So this is actually a case of a removable discontinuity. They've taken the one hole and they've created a second equation for that particular x value. Let's fill in the hole and plug it in at exactly the right spot so that this function is continuous where if you have the first fraction, remember, has basically a straight line, that's all it is, with a hole in it. They've filled in that one hole, so now this function is continuous everywhere. Let's write that down. So f is continuous everywhere because the point -2, 1 fills in the hole. All right. So that's a bunch of examples for you of what to watch out for. As we go through the course, we'll see some more practice problems, but I've given you pretty much what you need to be able to complete your homework. So good luck, practice, have fun, study hard. See you in the next video.